with all the chapters, and today we're going to do a review, and next class is the final class. We'll also do the review. So I tried to summarize everything on one page. So if you're given a problem in the class, in the exam, how do you go about thinking about solving the problem? And this is a lot of wording here, but essence is to follow an elimination approach where you ask yourself some questions, and if you get, for example, in the first part, you try to figure out if it's a kinematics problem. If it is a kinematics problem, you apply kinematics equations, go on. If after so I'm going to go through this very quickly, but this is a lot of material, so don't, if you don't get it first time, it's okay, you should go and read it. So this is how I would recommend you solve problems. So first, figure out if the problem has only a velocity and acceleration to it. If it has, then it is the first two chapters. Okay, you don't have to do anything related to kinetics. Now it gets harder when you see that there are forces, given masses, and so on. So if the question is object moves a certain distance, or so velocity when the object moves a certain distance, or you're given the distance and you're told to find the velocity, then you got to think in terms of conservation of energy and work energy. Okay, so this is, you're told to find velocity and you're given distance, or s, or vice versa. The third point is, if you're given velocity and told to find the time, then it's a problem in which you got to apply linear and angular momentum impulse equations. Okay, and if 2 and 3 doesn't work, then this technique will always work, which is use equations of motion. In fact, if you are blanked out in the exam and you don't know what to apply, 2 or 3, just write equations of motion. There's usually a way to solve the problem that way. Sometimes it's not possible to solve it analytically, but you will be able to do a lot of work, if you just apply equations of motion. And clearly 2 and 3 are easier ways of solving the problem, and 4 is perhaps the hardest one. If there's a problem of this nature, then 2 and 3 works pretty well. Okay, so read through this. This is a lot of stuff in here, but what I will do today is essentially follow this particular approach to solve problems. I'll go 1 all the way to 4. Okay, and by the way, there are some exceptions. The exceptions are, there's an exception here. Underline it with red. And there's another one here. So if those exceptions are true, then you cannot apply 2 or 3. You have to go for 4. And I think there's one problem where I'll show you that where the exception comes. Okay, so okay, let's read this question. The force F acting in a constant direction on the 20 kilogram mass. So this is a 20 kilogram mass. Has a magnitude which varies with position. So force is a function of position. Determine how far the block must slide before its velocity becomes 15 meters per second. When s equals 0, so s equals 0, let's call it s1, the block is moving to the right with a velocity of 6 meters per second. So you're going to find S2 when the velocity is 15 meters per second. Okay, and there's mu k. Okay, so the block is not at rest, it's moving with 6 meters per second. When the distance is 0, that's when you start measuring distance. Then this force is applied, which is clearly not constant, function of distance. You're going to find the distance S2 when the velocity is 15 meters per second. The key thing to note here is that you're asked to find velocity, you're told to find the distance when the velocity is 15 meters per second. Okay, so velocity is a function of distance. What will you apply in this case? So, well, there are two things you could do. One is principle of work energy or conservation of energy, right? Conservation of energy is good when there are conservative forces like gravity, springs, and so on. In this case, there's one thing is this friction, and the other thing is that force F is not conservative. So this implies that we're going to use principle of work energy. Okay, so what has been said throughout this course is true, which is always draw a free body diagram. There's always some credit for that. It doesn't hurt to draw a free body diagram, unless of course it's a kinematics problem where you don't need a free body diagram. There are no forces involved. And friction is this way. Okay, so principle of work energy states that I think it's T1 plus summation U12 is T2. So initial energy is half mv1 square plus the work done is the work done. Well, there are four external forces. There's F, Ff, mg, and n. Of these four forces, two forces, n and mg, did not do work because the particle is not moving in the y direction. It's only moving in the x direction. So the only forces of interest are F, and F. So F times ds, and our convention is F is to the right and S is to the right. So that's positive. S1 to S2. Friction force is acting in the minus x direction. And our convention is F ds is positive because the positive direction is to the right. So this is going to be F minus Ff ds equals the final kinetic energy, that's mv2 square. Okay, Ff is mu k times the normal force, and the normal force is mg. So what I have here is the integral of F is 50 S to half minus mu k m g times ds is half v2 squared. Okay, which is half mv1 squared plus 50 integral of s raised to half is s3 divided by 2 divided by 3 divided by 2 s2 s1 minus mu k mg s2 minus s1 equals half mv2 square. Okay, so this is 50 times 2, okay, so it's 100 divided by 3, S2, 3 divided by 2, minus S1 is 0, minus mu kmg S2 equals half mv2 square. Okay, so everything over there except for S2 is yeah, S2 is unknown, V2 is known. Right? It turns out that when you try to solve this equation, you'll actually get an equation which is S cubed, and I don't think you can solve it using a calculator. You'll need to use like a Newton-Raphson, something you run in numerical methods. Now, most likely the way will give you this question. So if that happens, then you're free to keep it in the final form and say that I'll solve this numerically. But if that, a better way to give this problem, and this from the book, is to actually give you S2 and ask you to find V2, because if you put in the value of S2, V2 is just square, so it's easy to solve. But most likely you will not see a question where you got to solve an equation which has S2 as an unknown, where you have 3 divided by 2, and of course there's an S2 here, so it's not really a quadratic equation. Okay? If you solve this, S2 comes out to be 20.5 meters. Okay, but as I said, the final answer is not important. What's important is that you set up the equation right. Now, as I said, if you forget how to, you say you don't quite remember how to solve this using principle of work and energy, then you're free to use the equations of motion, F equals ma, and they will also give you the same answer. So I'm going to try to do this same problem using equations of motion. So another way, equation of motion. Okay, so that is Fx is mass times acceleration in the x direction. The net force is F minus Ff. As you can see here, F minus Ff equals mass times acceleration. Okay, now F is 50 s raised to half minus mu k mg equals, okay, now if you write on new line, so 50 s raised to half minus Ff is mu k mg equals m. Okay, now I need to write the acceleration in such a way that I can use acceleration to find the velocity, right? Eventually I'm interested in finding s as a function of velocity. So would this help me? So if I do this, then what will happen is dt will come up here, but then I don't know what s is as a function of time, so this will not work. Is there anything else I could do? So it's v dv ds is a better way to do this, right? So what you get here effectively is 50 s raised to half minus mu k mg ds. S2 S1 is integral mv dv v1 v2, and this thing on the left side is half mv2 squared minus m v1 squared. So the thing to note is that this over here is the same as it over here. These expressions are the same, right? They are identical. So if you continue doing it, you'll end up getting the same formulas, and your answer will be the same, except that you will not be able to solve it with a calculator because of the s cube here. Okay, so here is a problem where you could solve it either way, and perhaps The first way is simple because you don't have to really remember how to do this about the substitution. But then once you know that substitution, it boils down to the same formula. Is that clear? Any questions on this? Okay, so I slightly twisted the problem. Same problem, looks similar, but in this case, so the wording is the same, but what I said here is determine the time the block must slide before its velocity becomes 15 meters per second. So earlier you were asked to find the distance when the velocity was 15 meters per second, and you told that when t is 0, the block is moving to the right with 6 meters per second. So I'm going to set up the unknown. So t1 is 0, the velocity is 6 meters per second. At t2, which is unknown, v2 equals 15 meters per second. Okay, so thing to note here is the unknown, the time is asked, and you got to find when the time when the velocity reaches a certain value. So here you're asked to find velocity as a function of time. So what would you use? Impulse and momentum, right? So just based on that, this is a problem on impulse and momentum. Okay, so there's an FPD, see previous page. Okay, now we'll draw that again. Principle of impulse and momentum is what's the principle of impulse momentum? It is mv1 plus f dt equals mv2. mv1 plus the net force is 50 t raised to half minus friction force, which is mu kmg dt t2 t1 equals mv2. Okay, so mass is known, v1 is known, v2 is known, m is known. You could, well, this, let me just write this down, but this is exactly the same expression as the previous one, except time is replaced with, s is replaced with t. This comes out to be 50 t raised to 3 by 2 t2 t1 minus mu k mg t2 minus t1 is mv2, and so get mv1 plus 100 divided by 3. t1 is 0, so I'm going to write that down. t2 minus mu kmg. So v1 is known, v2 is known, mg is known, mu k is known, t2 is an unknown, so I'm missing t2, sorry. So t2 is unknown, and when you try to sub in the values, you'll again get an equation which will have a t raised to cube, and you cannot solve it using a calculator, so you should keep it as it is. In fact, you get something like this: 10t 3 by 2 minus 18 t2 equals 27. And the issue is that this is a t3 divided by 2, and that's why it's hard to solve it using a calculator. So this needs to be solved numerically. Okay, I don't have the answer, but it's absolutely fine if you write it this way. This needs to be solved numerically, and you don't have to solve it. But in this question here, you saw that you could do this using impulse momentum, but it's absolutely fine to do the same problem using equations of motion. So I will not do this, but you could do this, use equation of motion. Okay, you should try this out and see if you get the same answer. Do you have any questions on that? Okay, next question. The disk, which has a mass of 20 kilogram, is subjected to the couple moment of m equals 2 theta plus 4, where theta is in radians. If it starts from rest, so theta 1 dot of velocity is 0, starts from rest, determine its angular velocity. Let me write this as omega 1 is 0. Find the angular velocity when it has made 2 revolutions. So theta 2 is 2 revolutions, which is 2 times 2 pi. 1 revolution is 2 pi radians, so it's 4 pi is the angle turned, and theta 1 is the initial angle, that is 0. Okay. So in this question, you're asked to find omega 2 when you're given theta 2. So how do you solve this? What principle would you use? Would you use impulse momentum? When you ask position as a function of speed, you want to think of work, energy, or conservation. You only want to think of impulse momentum when you ask velocity as a function of time. So in this case, principle of work energy is more ideal. So let me start. So this suggests that you need to use principle of work energy. And not conservation, because there is a non-conservative force. We don't know what 2 theta plus 4 is. It's actually non-conservative. So let us draw the free body diagram of the disk. X, Y. So I think in this case you assume that theta positive is this way. At least that's what it seems from the figure. So this is positive theta, and the reaction forces are OY, OX. There is a moment M, and there's mg. Okay, so principle of work and energy. Okay, states that, so it's a principle of work energy for the disk. So it's T1 plus summation U12 is T2. That remains the same. However, T1, as somebody pointed out, is not half mv squared, right? Because it's not a particle, it's a rigid body. So T1 is half IO omega squared, omega 1 squared, the final energy is half I O omega 2 square. And very intentionally I took the energy about, well, the axes are about O, because in the work done I do not want the OX and OY to show up. So the only way I can do that is by taking the inertia, choosing the axis to pass through O. So the only force which matters, or the only couple or the torque which matters in this is m d theta, where m is the external torque. Okay, so theta 1, theta 2. So for a disk, the inertia is mr square divided by 2. I'm going to give that to you, so don't worry about it. This is mr square divided by 2 omega 1 square plus 2 theta plus 4 integral from theta 2 to theta 1 Okay, so this integral comes out to be 2 theta squared divided by 2 plus 4 theta, so that cancels off. So what we are left with is half mr squared divided by 2 omega 1 square plus, putting theta 2 and theta 1 is 0, gives me theta 2 square plus 4 theta 2 equals half m r square divided by 2 omega 2 square. Okay, so in this case, mass is known, radius is known, the angular speed omega 1 is known, it's 0. Omega 2 is the unknown, this is the unknown, and theta 2 is known, right? So only unknown is omega 2, so you can solve for omega 2. The answer is 21.5 radians per second. Okay, can you think of an alternate way of solving the same problem? Okay, you can always, as I said, use equations of motion. So another way is to use equations of motion. Okay, which is which equation of motion will you use in this case? Some of the moments about the point O. Okay, and this is a case of rotation about an axis. So remember, there are 3 formulas in that chapter. One was translation motion, there's no rotation. In this case, summation of moments is equal to 0. This is the case where it's rotation about fixed axis. This is the case when it's fixed axis. The third one was general planar motion, where the point of the axis need not be moving at a uniform speed, or it may not be at rest. So in this case, it's fixed axis. So MO is simply 2 theta plus 4 equals, the inertia is mr square divided by 2, and we need to basically, we need to find not alpha, but we need to find what, omega. So we need to write alpha as a function of omega. So will this work? So this will not work, because when I move dt to the left side to integrate, I'll have integral theta times dt, but I don't know what theta is as a function of time, so I can't use this. So then I have to use omega d omega d theta. This is exactly same as the linear analog v dv ds. Okay, so 2 theta plus 4 d theta, theta 1 to theta 2 equals mr squared divided by 2 omega d omega from omega 1 to omega 2. So this is half mr square omega 2 square minus omega 1 square. And if you see this is the same as this expression here. It's identical except that things have been moved around. Okay, so you get the same, you basically start getting the same thing here and get the same answer. Okay, is that clear? Any questions? Questions? Okay. Okay, now I have the same question, but I've slightly changed the problem. So the moment is the same, okay, mass is the same, but I've asked you to find the time when the angular velocity will be 10 radians per second. Okay, so T1 is 0, omega 1 is 0. You got to find the time when angular velocity is 10. Okay, so, well, if you're asked to find speed as a function of time, it seems that you need to use principle of impulse momentum, right? FBD, same as previous. Okay, principle of principle of impulse momentum. Which says that H, what's it, H O1 plus m dt equals HO2, right? Is that right? Yeah. So I O omega 1 plus 2 theta plus 4 dt equals I O omega 2. Okay, can you do that integral? Theta is not a function of time, and you have to find theta as a function of time. So here is a case where blind application of principle of impulse and momentum, even when this looks all right, will not work, because the m is not a function of time. If m was a function of time, like if you went slightly back when we did this problem, right? Here, this was a problem of, sorry, not this one, this one. Here, f was a function of time, and we were asked to find v as a function of time. This worked perfectly because right here we could integrate f dt, but in this case you cannot integrate m dt because m is a function of theta. So this is not going to work. It won't work. So I have actually put it in the exception. If you see that m is a function of theta, if you're told to find v as a function of time and the external force is a function of theta, then you cannot apply impulse and momentum. You have to resort to the last option, which is the equations of motion. So this does not work because m dt is 2 theta plus 4 dt cannot be integrated. Okay, so let's resort to equations of motion. So this is fixed axis. Moment about O is I O alpha, right? MO is 2 theta plus 4 equals IO. Now, I have a couple of options. Well, two options really. I could do d omega dt. Will this work? Because again, if I move the dt around to integrate, I'll have the same thing which I got previously. I cannot integrate 2 theta plus 4 times dt because theta is not given as a function of time. So I'm stuck with this. Now I could, because theta is, I can move the theta around and integrate the moment, right? So 2 theta plus 4 d theta. And when you're doing this integral, you want to be careful. You don't want to integrate from theta 1 to theta 2. You do not know what theta 2 is. So you want to integrate for a general theta, and you'll see why. Equals IO so initial position is 0, initial time is omega is 0 to omega. So this comes out to be, I'm going to skip a step and I'm going to jump to the final answer, but you should try to do it slowly. So this is theta square plus 4 theta, okay, equals m r. So I'm going to write it here. So skip steps. Okay, mr square omega to omega square divided by 2. Okay, but that doesn't help me, because eventually I need to find omega as a function of time. Okay, so to do that, what I need to do is I'm going to move things around. This is 2 times 2 is 4 divided by mr squared, theta square 4 theta equals omega square. So I can do it this way. So I wrote omega as a function of theta, okay, with the hope that now I can do omega is d theta dt, and then integrate this expression to get theta as a function of time. So this comes out to be, I'm going to move this dt on the other side. D theta down. Is that?
I have no idea.
Write it, okay. Perhaps I'll write this. Theta square plus 4 theta equals mr square. Is this fine? I took the square root on both sides first. Okay, so I just kept it this. Now I wrote this omega as, and now I'm going to move the dt to the left and theta square plus 4 theta down. So dt is this better? Do you know how to integrate this expression, theta square plus 4 theta? We'll try it later. Okay, okay, so it just turned out this problem came out to be this complicated integral. Don't worry about it. You will not be getting an integral like this. But my purpose of doing this is to show you not really the math of how to solve the problem, but to show you that something like this cannot be done using the usual way. So this comes out to be, you actually need to complete the squares on this and then solve it. So it comes out to be log of theta plus 2 plus square root theta square plus 4 theta equals square root 4 mr square t. So the key thing is that here you have an expression for theta as a function of omega, and here you have an expression for theta as a function of t. So from 1 and 2, so from 1, solve for theta when omega equals what? 10, right? And then from 2, solve for t when, so this gives me theta equals, I get 0.915, okay? When I solve for theta when omega is 10, I get 9.5. So then I need to do is solve for t when, using 2, when theta equals 0.915 to get t equals 1.08. So what I've done is I've solved for omega as a function of theta first, and then solved for theta as a function of time because I know. So the integration is complicated, but if you get this kind of problem, I assure you it won't not be a complicated integration. If you do see that, if you do end up getting a complicated integral, please feel free to write there. I would do this and just lay down the steps. Don't try to solve it if you are not comfortable, because this is not going to carry much weightage in the exam anyway. So 10% of your total credits. Okay, so I have. So is this clear? So again, when I'm solving this, I'm using the first page I gave you a recipe. I'm actually going through that recipe to solve this. The last problem, and I what's the time? 4 minutes. Okay, I think I should not solve this problem, but let you solve this problem. Can you read the question and tell me what question this will be, what principle you'll use? So determine the constant speed at which the cable A must be drawn by the motor in order to hoist the load 6 meters in 5 seconds. So, okay, I think this thing is spinning so that A is moving at constant speed down. That's not given if it starts at rest. I believe it's at rest, yeah. I don't think you can do it without assuming that. So given 6, this should move 6 meters in 1.5 seconds. So assume it starts from rest. So the initial velocity is 0, it moves 6 meters, 1.5 seconds. You've got to find the speed at which A should move. Okay, so it's what? Kinetics or kinematics? It's kinematics. So one way to guess is that you are not given any mass. There's no mass given to you. You cannot use F equals ma in this equation. So it has to be a non-kinetics problem. We could have confused you by giving you the mass. Got to be careful. Okay. Gravity is not given too. What else? So sometimes they give you hints, but sometimes they may try to trick you. Don't get tricked. Okay, so this is a pure kinematics problem. The other thing to differentiate is between a particle and a rigid body problem. Okay, and the way to distinguish that is for rigid bodies, we'll invariably tell you radius of gyration or we'll give you the inertia. If it's a rigid body problem, the application of the location of where the force is applied is very important because that determines the moment. You cannot just assume wherever you want the forces. So you got to be slightly careful when you do rigid body problems as opposed to particle problems because the point of application of the force is important. So the review today was covered principle of work, energy, impulse, momentum. Next time, I think I'm going to do something slightly different. I think I'm going to do, I forget what I'm going to do. I think it's going to be problems where you have to apply multiple approaches, multiple concepts, something like that. So I'll see you on Friday.